Now, I'd like to look at this kind of bird's eye view of what's involved in coming up with what the concentration of our solution is and what's the implication for the concentration of the respective ions. So as mentioned, the calculation involves taking that mass and converting to moles. So that's what we did. And then we're going to take those moles and divide by the volume in liters. So that's what we did. And we came up with a concentration of 0.420 molar. So that's the concentration of our magnesium chloride. But again, I want to emphasize that there is no magnesium chloride in our solution because it's all in the form of magnesium ions and chloride ions. But we know what the concentration of those respective ions are, because for every one magnesium chloride unit, there's 1 mole of magnesium plus 2. So therefore, the concentration of magnesium ions is equivalent to what we thought would be the concentration of magnesium chloride. And in a similar way, the concentration of the chloride ion would be double, because for every 1 mole of magnesium chloride, there are 2 moles of chloride ions. So understand that if you do the calculation to determine the concentration of magnesium chloride, you also know what the concentration of magnesium ions are and also the concentration of chloride ions. And of course, we could work backwards. If we find that the concentration of chloride ion is 0.840 molar, well, in turn, we know what the so-called concentration of magnesium chloride would be, as well as what the concentration of the magnesium ions would be. So as a little bit of practice, I ask you to take a look at exercise number 1. Determine the aluminum ion concentration and the chloride ion concentration in a 0.125 molar aluminum chloride solution. So I ask you to pause the video, but as a little bit of a hint, you don't need the molar mass of aluminum chloride here. So hopefully you pause the video. I'm using the equation for the dissolution of aluminum chloride, producing aluminum ions and chloride ions. And as I mentioned, you don't need the molar mass because we're already working at the level of molarity. So as it turns out, if you know the concentration of aluminum chloride, 0.125 molar, well, for every 1 unit of aluminum chloride, 1 unit of aluminum ions are produced. So the concentration of aluminum ions is 0.125 molar. In a similar fashion, the concentration of chloride ions will be 3 times that value. Again, for every 1 aluminum chloride unit, there are 3 units of chloride ions. We'll do some of the other calculations in this activity in our live sessions. I'd like to move on to the next concept. So actually, the idea of concentration in units of moles per liter introduces to us a new conversion factor. So the diagram on the left should look at least in part familiar to you, because we've already looked at the idea of mass to amount conversions. And as you know, in order to make these kinds of conversions, you need to use the molar mass. Well, if we have the volume of an aqueous solution in liters, we can also convert that to the amount of substance. And all we need is a concentration. And so our concentration will be the appropriate conversion factor. So up until now, so far in doing stoichiometry, we've had to have given you a mass of the chemical and you had to convert that to moles. Well, now we can give you a volume of solution and a concentration, and you can also convert that to moles. For example, if we were to say determine the amount of lead nitrate in moles contained in 25 mils of 0.0125 molar solution, well, we've got a volume and we have a concentration. So I highlight that, remember that capital M is equivalent to moles per liter, and we have the volume in 25 mils. Now note, we need the volume in liters. So a unit plan might look something like this. Volume in mils, and we're going to convert that to volume in liters, so essentially just divide by 1,000. And then we'll use our concentration to determine the amount in moles. The actual calculation will look something like this. 25 mils divided by 1,000 mils times our concentration, our conversion factor. Now note, I say formula units for lead nitrate because, again, these are not molecules, these are ions. And then, of course, we end up with the amount, 0.0312 moles of lead-2 nitrate. As a little bit of practice, let's take a look at this calculation. Determine the amount of nitrate ions in moles in 250 mils of 0.1456 molar iron 3 nitrate solution. I indicate first show a unit plan and do the appropriate calculation. Note, in this case, we're asking for the amount of nitrate ions and not the amount of iron 3 nitrate. So perhaps before you start the calculation, let's do the unit plan together. You're starting with a volume in milliliters. You're going to change that to a volume in liters. You're going to use the conversion factor of concentration to change to the amount of iron 3 nitrate. And then if you know the amount of iron 3 nitrate, well, then you know the amount of nitrate ions. So I encourage you to stop the video and see if you can do this calculation. So the calculation would look something like this. I take the volume in milliliters and divide by 1,000. So now I'd have a volume in liters. And by the way, if you're comfortable doing that calculation just in your head, then go ahead. So that would be 0.25000 liters. Then we multiply by the concentration of our iron nitrate solution. And then we use the ionic formula, understanding that there are 3 moles of nitrate for every 1 mole of iron 3 nitrate. And now we know the moles of nitrate ions. The last part of this video tries to make connection with the other kinds of stoichiometry that we've done so far. So I'm hoping that you're feeling pretty comfortable with the upper part of this diagram, which involves mass to mole to mole to mass relationships. And you know the conversion factors that are involved. The molar mass between mass and the amount of substance. And of course, the mole to mole ratio within a balanced chemical equation, the so-called mole bridge, if you will. Well, now we know some new conversion factors, that is the concentration. So if we have volume of solution and we have the concentration, we can determine the amount of substance. So now there are a number of different kinds of calculations that can be done. So for instance, you could be given the volume of a solution of chemical A and its concentration and asked to determine what mass of chemical B would be produced as a result of the reaction. Let's talk through a worked out example, and then in our live sessions, we will do some more examples. Let's read through this question so that you're clear on what's going on and what are the signs that you need to pay attention to the fact that this is a solution kind of question. So I see, calculate the mass of barium sulfate solid that can be made from, so I know that involves mass, but then it says 10 mils of 0.125 molar barium chloride. Oh, okay, that's a volume and a concentration. So I'm starting with a volume of a solution, and I have the concentration. Oh, and I'm told I have an excess of 1 molar sulfuric acid, so I already know what the limiting reagent is. So I'm given the balanced equation. And as I've encouraged you to do, use the balanced equation to organize your information. So under the barium chloride, I write the volume of solution. I've already changed the volume in mils to a volume in liters. So 0.01000 liters. And then the concentration. I write that we have an excess of sulfuric acid, so highlighting that the barium chloride is limiting. And I highlight the fact that we're looking for the mass of barium sulfate. You can see that I write out a unit plan. The volume of barium chloride to the amount of barium chloride to the amount of barium sulfate, and then finally the mass of barium sulfate. And then what's shown in gray would be the actual calculation. The volume times the concentration, of course, will give me the amount in moles of barium chloride. Now in this case, the balanced equation shows us 1 mole of barium sulfate is produced from 1 mole of barium chloride. Of course, it could be any sort of ratio based on the balanced chemical equation. And then finally, instead of trying to find a certain volume of solution or concentration of a solution, I'm asked to determine the mass. So I'm going to need to use the molar mass. So as mentioned, in live sessions, we'll do some more calculations involving stoichiometry, involving aqueous solutions and mole mass and concentration, volume of solution, types of interconversions.